The function f of x equals 2x cubed plus 3x squared plus bx plus c has a local maximum at x equals minus 2. In the first question, we want to find the value of b. Well, a local maximum is a turning point. So at minus 2, we have a turning point. And it's a local maximum turning point. So at minus 2, our curve could look like this. It could be below the x-axis as well, of course. We don't know that yet. We don't have it. Haven't looked into that yet. But at minus 2 anyway, we can see that we have a turning point. So we know that the slope of this tangent, which is the derivative of the function at minus 2, must be 0. So we look at the derivative of the function with respect to x. We get 6x squared plus 6x plus b. The derivative of c is 0. And we know that this derivative evaluated at minus 2 must give 0. So 6 times minus 2 squared plus 6 times minus 2 plus b must equal 0. So we have plus 24 minus 12, plus 12 plus b equals 0. So b equals minus 12. In part 2, we want to find a range of values of c for which f of x equals 0 has 3 distinct real roots. So I've written down f of x here now. Replacing b with minus 12, we found out what b is. We don't know what c is. But we want this function to have 3 distinct real roots. Now, the only way that can happen is if the local maximum at x equals minus 2 is above the x-axis. Because if it was below the x-axis, suppose the local maximum at minus 2 was down here, well then the curve would look like this. It would only cross the x-axis at one point. It would only have one real root. It doesn't have to cross it there. It could also cross it up here. You see, we're dealing with a cubic function. A cubic function has at most 3 distinct real roots. We're given that this one has a turning point at minus 2 and has a local max of minus 2. So you can see that the turning point cannot be below the x-axis, because if it was, we would only have one real root. So the turning point has to be above the x-axis. You see, when the turning point is above the x-axis, the curve will have a root here, and it may have another. Hopefully it will cross it at 2 more points. We want the function to have 3 distinct roots. So this is the situation. We must have this point above the x-axis. We have no hope otherwise. Of course, it's possible for the local max to be above the x-axis and still only have one root. You know, it could look like this, or we could have 2 roots, in which case it would look like this. Of course, we want this situation. But first of all, we have to ensure that f of minus 2 is positive. So this is f of minus 2. We want f of minus 2 to be greater than, it has to be greater than 0. It can't equal 0. If it equals 0, we would have this situation here. We would only have 2 roots. You know, if f of minus 2 was equal to 0, the curve would just touch at minus 2. So we can say that a necessary condition for f of x to have 3 distinct real roots is that f of minus 2 must be greater than 0. This is a necessary condition. It's not a sufficient condition. Okay, as I explained earlier, and I'll just explain it again quickly. If f of minus 2 is positive, we could still have this situation. F of minus 2 is positive here, but you see we've only got one root. But it's a necessary condition. So we'll take care of this condition first of all, and then we look at other conditions that we need. So working out f of minus 2, what do we get? We plug minus 2 in here, and we set it, f of minus 2 to be greater than 0. And if you do this calculation, you will see that c has to be greater than minus 20. So this is a necessary condition for f of x to have 3 distinct real roots. Another necessary condition for the function to have 3 distinct real roots is that the local is that the local minimum is below the x-axis. So we must have the local max above the x-axis, we must have the local min below the x-axis. Then we will have three distinct real roots. So let's look at the coordinates of the local min and local max. Well, to do that, we set the first derivative equal to 0, because at a local max and a local min, the tangents are horizontal lines, their slopes, f prime of x, are 0. So if we solve this, we can find the x values of the local max and local min. So all I did was just differentiate this, and you can see that c will drop out when I differentiate this. So we need to solve this quadratic equation. We can divide it all by 6. We can factorize it. Let's see now. X plus 2 times x minus 1 equals 0. Okay, I think they're the correct factors. Yes, indeed they are. So we've two x values. We have x equals minus 2 when we put x plus 2 equal to 0. When we put the other factor x minus 1 equal to 0, we get x equals 1. So at x equals 1, there must be a minimum turning point. We know that at minus 2 we have a local max. Now, let's look at the coordinates of this local min. We want this local min to be below the x-axis. To get the coordinates of the local min, we have to find f of 1. The x value is 1. To get the y value, we get the value of the function at 1. So here's our function. So we need to plug 1 into this function here. And that gives us f of 1. So we can do that mentally. If we plug 1 into this, what do we get? We get 2 plus 3 minus 12 plus c. That's 5 minus 12, which is minus 7. We get minus 7 plus c. We want this point to be below the x-axis, so we want minus 7 plus c to be negative. It has to be less than 0. To be some negative value. So we put minus 7 plus c less than 0. We solve this inequality. Bring the minus 7 over. We see that c is less than plus 7. So we have the two necessary conditions. If we put these two necessary conditions together, we see that the sufficient condition for f of x to have three distinct roots is that c must be greater than minus 20 and it must be less than 7. So if c lies between minus 20 and plus 7, then we have three distinct roots to our function. The function f of x equals 1 plus x log to the base e of 1 plus x is defined for x greater than minus 1. Well, it has to be defined for x greater than minus 1, because when x is greater than minus 1, then 1 plus x will be greater than 0, as long as this is greater than minus 1. Because we can't get the log of 0 and we can't get the log of a negative number. So x has to be greater than minus 1 to ensure that this is positive. Okay, that's just a small point. We want to show that the curve has a turning point at this point here. Right. Now, let's get the first derivative. To find turning points, we put the first derivative equal to 0 and we solve. We have a product of functions here. U is 1 plus x, v is ln of 1 plus x. So we have the derivative is u multiplied by dv dx. So if we differentiate this, we have to use the chain rule. When we differentiate ln of something, we put 1 over the argument. Then we multiply by the derivative of the argument. The derivative of 1 plus x is 1. So this is u dv dx. Then we have plus v times du dx. Well, v is 1 plus ln of 1 plus x. We multiply that by du dx. The derivative of 1 plus x with respect to x is 1. We put this equal to 0. So we take one function times the derivative of the other function, plus the other function times the derivative of the first function. That's the product rule. These cancel out, so we get 1 plus ln of 1 plus x equals 0. And we can solve this to get ln of 1 plus x equals minus 1. Ln means log to the base e. We can write this, just to make it clear, I'll write this as log to the base e. So basically we have a single log term here, we have a number on the right hand side. So that means if we put e to the power minus 1, we get the argument. So 1 plus x equals e to the power minus 1. So x equals e to the power minus 1 minus 1. This can be written as 1 over e minus 1, which if we get a common denominator, we get 1 minus e over e. See, we have 1 over e minus e over e. E over e is just 1. So we can write it like this. Notice that there is only one solution to this equation, f prime of x equals 0. We did not get a quadratic equation. We just have a linear equation in x, and we get one solution. So that tells us that there is only one turning point of this function here, of f of x, and it occurs at x equals 1 minus e over e. If we want to find the y value of the turning point, we want to evaluate the function at 1 minus e over e. So we plug in 1 minus e over e for x, and we need to evaluate this. Let's see now, 1 is just e over e. So we've e over e plus 1 minus e over e. So we've e plus 1 minus e. That gives us 1 over e. So 1 plus, so this here breaks down to 1 over e. Then we have ln of e over e plus 1 minus e over e. E plus 1 minus e is 1. So we get 1 over e times ln of 1 over e. Well, that's just 1 over e. I'll just write ln as log to the base e to make it clear. E to the power minus 1 over e is actually e to the power minus 1. So you see here we have 1 over e. Log to the base e of e to the power minus 1 means what power must we raise e to in order to get e to the power minus 1? Well, the answer is minus 1. Another way to see this is to use one of the rules for logs, and that is we can bring the power down in front. So we multiply minus 1 by 1 over e to get minus 1 over e. Then we have log to the base e of e. Well, log to the base e of e is just 1. That's another way you can see it. So the x value of the turning point is 1 minus e over e, and the y value is minus 1 over e. In part 2, we want to determine whether the turning point is a local max or a local min. Now, as I explained in a previous video, to determine the nature of a turning point, we need to consider the second derivative of the function at the x value of the turning point. If the second derivative is positive, we have a local minimum. If the second derivative is negative, we have a local maximum. So we need to get the second derivative. So here's the first derivative. So we differentiate it again, differentiate 1, we get 0. When we differentiate ln of something, we get 1 over that something times the derivative of the argument. Well, the derivative of 1 plus x is 1. So we just end up with 1 over 1 plus x. And what we need to do is get the second derivative at the x value of the turning point. So we want to plug in 1 minus e over e for x, and then see the sign of this thing, see if it's positive or negative. Okay, to simplify this, the best thing to do is multiply above and below by e. E times 1 is e. Multiplying e by the denominator, we have e times 1 is e. E times 1 minus e over e, well, the e's will cancel, so we get this for our denominator. E times 1 is e. E times this fraction is 1 minus e. Well, these e's cancel out, so we get e over 1, which is e. Now, is e a positive or negative number? Well, we know that e is 2.7 to 1 decimal place. It's a positive value. So the second derivative at the x value of the turning point is positive. So that tells us that 1 minus e over e, that this turning point here, is a local minimum. Here is a sketch of the function. The turning point, the x value of the turning point is actually negative, because e, remember, e is 2.7. So we have 1 minus 2.7. Well, e is approximately 2.7. 1 minus 2.7 is minus 1.7. So we have minus 1.7 divided by plus 2.7. So this will come out to be negative. And this y value is also negative. So we have a point down here, down in this quadrant here. And it's a local minimum. So I have this upside down. Now the graph must look like this actually, because it's a local minimum. And we've already explained that there is only one turning point. You know, when we solved the equation f prime of x equals 0, we saw that there's only one solution. One value of x. 1 minus e over e was the value of x. So there's only one turning point. So the graph can't turn back down again. So, you know, if it was to go back down again, then we would have a second turning point. We would have two solutions to f prime of x equals 0. We've only got one solution to f prime of x equals 0. So the graph must keep continuing on indefinitely in these directions.